Today I'm going to present the para-virtualization of the AMD NPU. There is an echo that's going. It has to be, yeah, this is fine. And just give me, yeah. Yeah. That's great. Oh, excellent. Okay. Thank you. Thank you so much.
So other than the production flow, I guess again. It's even harder.
You know that sounds different. You speak name, subject. We're good.
Hello. Hello. It's echoing.
Maybe I can just remove this. Yeah.
Directly.
Yeah, I can speak loud. Is that good? Oh, still echoes?
It's still echoing.
Keep going. If things, maybe say something.
Hello? Yeah, echoes.
Is there a hot light?
Maybe mute the Mac.
I asked.
Huh?
Why can't you mute yourself?
No, but if I mute, then the remote people will not.
Test,
Hello.
test, 1, 2, 3. I think we're good.
Okay, sounds great.
Share. Share screen. And let you on your laptop.
This is the one. Share. Yeah.
Good. Okay. Okay, finally. Okay, other than the production flow, we have a open source flow for the NPU software stack. So you can see that from the user space application, you have an open source compiler, and also open source runtime, and also a driver. The entire flow has been open sourced on Linux. And the driver is also included, upstreamed to the Linux kernel start from the 6.14. So so these slides briefly talk about the NPU execution flow. So from the top to the bottom, you can see that's the behavior of the user space, kernel driver, and the NPU hardware and firmware. So from the left to the right, for the user space, the compiler compile the user code to a control code that hardware can recognize. Then the application gonna to create some buffers, which is accessible by the hardware. Then those control code will be put into those buffers. Then the last step is this buffers can be submitted to the hardware to real process it. So from the top to the bottom, you can see each step like compile control code based on the application requirement. It can unlock one or more AIE columns, which showed in the first slides. And at the same time, the hardware context being created by the firmware, which put all this resource bundled together. Then the second step, when you create a buffer, it actually reaches the kernel, Linux kernel DRM subsystem, which will create a buffer object. And you can put the control code, also the data into this buffer so the device can access. Then the last step is just submit this buffers and to the hardware context, then the hardware going to start to process the data. So I show this slides to for the following pages. You can see we actually have some requirements for the virtualization. So first, we receive more and more requests to virtualize the NPU device. So we got a better security and also the isolated environment for the applications. So potentially each application can run into its own VM. And also this will allow the single hardware can be shared among the multiple virtual VM, virtual machines. And also this para-virtualization technology enables better performance comparing to like fully emulation. And secondly, the current generations of the NPU hardware do not support the virtualization. So that means even we can potentially pass through the NPU to what? Okay. So even though the NPU can be passed through to a VM, but that means you pass through, then the hardware cannot be accessed by other VMs. So, and also unfortunately for this current release devices, SRV is not supported. So that's why we want a para-virtualized NPU. Then we also got some implementation requirements. Okay, I really can't use this. Help. Share button. This one. Yeah. Yeah, I got it. Yeah. Okay. Okay, we also got some implementation requirements. What we want to reuse the current QEMU and the Linux infrastructure, and also we want a unified solution for both Xen and QVM. And the last implementation requirements is we hope this this solution can be extensible to support the different accelerators other than the AMD NPU. So this is our solution. So for the previous slides, I talked about the execution flow for the NPU. So that's really like how the GPU be supported. So based on that flow, also we consider to use adapt this GPU what IO infrastructure for our NPU support. So from this chart, you can see the green box is what we are going to add for the NPU, and the white box is already been done actually by the GPU. So we leverage the GPU infrastructure. This benefits us for one, it's unified stack for both Xen and QVM because it is unified for GPU, so we automatically get it. And from the guest kernel, you can see we reuse the what IO GPU front end. So that means we do the zero change in the guest kernel. Third thing, the communication between the guest and the host side has been done by the GPU. We just wrap the NPU commands and messages with already implemented GPU message headers, and reuse this message channels and notifications is already been done by GPU. And the fourth one is like the memory mapping stuff is also being supported by the GPU infrastructure. We can map the guest memory to the host side by use the existing interfaces. So last thing is that we can also get an extensible QEMU backend, just like what GPU does. It has one front end, but multiple backend to support the different GPU hardware. We can do very similar implementation. So this is unique for our hardware, NPU hardware, to reach the best performance and security. The NPU need to use the SVM. That means the buffer virtual user space virtual address plus the length will be fit to the hardware, and hardware do the DMA directly by using the user space virtual address plus the length of the buffer. So this currently we don't have with the GPU infrastructure. So ideally, it needs to like be able to isolate the application inside the guest. But for current stage, we won't be able to provide that isolation. So the isolation will be bounded by the VM with the current implementation. So from the chart, you can see that if the guest memory will be used for alloc the buffer object. So you got a guest virtual address. Then in the guest kernel, you will see a scatter list of the guest physical address. Then this scatter list will be sent to the host. Then the host will get a uncontiguous host virtual address. So unfortunately, hardware only can accept a contiguous memory buffer with a host virtual address. So we have to remap this uncontiguous buffers into one contiguous buffer, which is a step 2. Then this address can be used to fit into the AMD NPU hardware. Then the hardware can use this host virtual address plus a pass ID to access the memory. The pass ID will be bundled to the QEMU process on the host side. So that's what I mean. It doesn't support the per process isolation at this time. Oh.
I'll stand here. Okay.
Okay, so this is almost a similar picture for Xen. So you can see the steps to the address translation is the same. It's 4 steps instead of because for Xen there is a dump 0. So in the DOM0, it has to support the virtualized LMU because the hardware relies on the SVM. So in DOM0, it has to support the pass ID so the LMU SV band device that function call to get a pass ID need to calls into Xen VLMU functions to get this pass ID. And using this is the same thing. It will be have the unified QEMU backend for both Xen and QVM because the key functions is already unified, like the DMA memory map calls. Oh, it's really hard to use. Okay, the last bullet shows device usage. Like you start a QEMU DOM-U in the DOM0, you just start the QEMU by adding this device, VirGL device. So this Excel 0 can specify which device you are working on. It can be exposed to the DOM-U. So this slide talks about a little detail for how the Xen LMU being supported. So the PVLMU is patches already been posted to this link I showing on the slides. By applying that, and it doesn't have the SVM supported with these patches. So SV enhancement has to be made on top of this patch. So another Xen team here. Implement some little bit detail for how this been added. So it will alloc the pass ID one binding device with a process that's and also is use the default context page table as a stage 2. Then created a CR3 by the pass IDs, etc. This is some detailed steps to add the SV enhancement on top of this PVLMU. So this slide showing the current progress for the VirGL NPU support. We already published this prototype to this link I provided, and with this steps showing in this GitHub page, you can run the VirGL NPU inside the KVM. The changes include the QEMU backend, and we also use the VirGL renderer plugin and the AMD XDNA. You can use the Linux upstream driver if you want for, and we hope all these changes will be pushed to the corresponding repos like QEMU VirGL renderer in the near future. For the Xen part, the prototype is work in progress. So currently, all this QEMU VirGL renderer and driver changes are ported from this published GitHub, and also it needs to apply this PVLMU stuff and enhance it to support the SVA. So the last slide talks about the challenges for this project. So the first one is how to do the per guest process isolation. That means we have to like generate pass ID for every guest process. And the one of the thinking is that we probably can use start a host process for each guest process that create maybe a shadow process to provide the isolation. Another thinking is that maybe we can modify the Linux kernel like to implement the malloc maybe to just create a page table without start a fork a new process. I don't know if that's possible. The second challenge is like the VirGL renderer backends. So if you are familiar with GPU stack, the VirGL render can only support like one device on the backend. So that means if you run the GPU and NPU export both. Yeah, that slide I can do it quickly. Yeah, fine.
It's a mess.
Too hard. Okay, so that means with the current VirGL renderer implementation, if you want export the GPU and NPU at the same time to the same VM, it doesn't work. So the one thinking is that instead of have the both backends in the same QEMU process, we can implement a vhost for the VirGL NPU. Then you have two backend process. Another thinking is that maybe we can upgrade the VirGL renderer itself to support the multiple backend inside the same process. The third challenge we have is that how to support the user point buffer in the guest. That means in a lot of use cases, a buffer is allocated by the application and then registered to the device, to the driver. That process is not supported by the VirGL GPU front end today. So maybe we can extend this VirGL GPU to support the user pointer buffer. So, okay. Okay, that's all for today. So any questions?
Sort of why you mentioned leverage bridge to implement the NPU start. And I wonder whether you would get aligned with the virtual stack. And there is one problem with the queue is a dependent device together with the GPU. So actually here you are trying to leverage the GPU command something for GPU side. That's probably where we see some concern to go to the upstream. So to the virtual stack, they need to create a new whether they need to create a new type history curve for NPU, virtual NPU here. So that's one of the things. Some strategy to create a virtual NPU to do a maybe both solution to contribute the virtual the design implementation here. Yeah, I believe probably if you try to go upstream, probably you are facing the same. So I'm not sure whether it's ready to go upstream or do the code.
We plan to go upstream. Yes.
But I think that is confirmed. That is but you probably want to go upstream, to contribute the virtual spec for the NPU's, the channels. They may receive this kind of concern.
Sure, we haven't started the upstream process yet. And from my learning on the GPU stack, every vendor has its customized command. And the VirGL GPU framework is actually just a wrap around the vendor specified command and send it to the, yeah.
Of course, you know, the internal GPU and the end GPU, or when we can have some part long, but this is not GPU for NPU.
Right.
You know, the virtual render is meant for the graphics, VRM, but the whole up level is messed up. You know, this is the strictly libraries.
Yeah.
It's a totally different stack.
Right, but they export the public interfaces on the layer, so we can chime in. We don't need to use the GPU runtime. They also the VirGL GPU driver export the ioctls. Ioctls you can call from different software, so our runtime can call the published GPU ioctls to achieve our goal. So I don't know if the open source community gonna against it or not, but this implementation is targeted on sharing, using the existing implementation as much as possible, so we don't create new problems, we don't introduce new issues. That might be the thinking right now.
Yeah, I can understand. And another problem is you just mentioned that they probably will conflict with the virtual GPU in one platform to working together in one, right?
Yeah, that's one of the challenge because yeah.
Yeah, that's the problem.
Yeah. Well, we hope.
Try to leverage the virtual GPU class, so override this class with NPU side. So that's the reason we probably need to create a new virtual device for NPU in virtual spec, then to put that type of farm always the NPU virtual NPU stack.
But it will be, the code will be too similar with each other. It's like if you implement a new like front end, like VirGL NPU, you're doing basically very the same thing for the VirGL GPU, as well as the backend. You implement a lot of things. It can be a lot of duplication. So you have to maintain the both very similar stack.
You want to take something?
You define you.
Yeah.
You know, the virtual, why they have a lot virtual, like for example, virtual net, virtual.
Oh yeah.
Okay,
You mean front end, right? You define the new one.
Yeah.
In the front end.
Yeah, for NPU probably need to find a new one backend.
Yeah, that's possible. That probably yeah, next step, or if it really required. But today, without even a single line change, it can already do everything for the NPU. So why we would add another one to do this? I don't have a strong. Yeah, but yeah. Yeah, maybe.
This is very good for the faster solutions, but in that probably you need to get go upstream and go forward. Probably we definitely need to go with the virtual spec to define this the why and this filter.
Yeah, probably the different device, but the same driver. I don't know the options is.
Right, but probably not. The other is ready for the upstream, SR, virtual render, they're all about 3D graphics. But I see you have this totally different the user space library.
Yeah, I think it's interesting that both Linux and Windows has the same challenge. You see how Axel subsystem came out of DRM subsystem on Linux. And in Microsoft, the MCB is being ordered on VirGL. So we all started as a GPU, but yes, specialization happened later. We'll probably have to take the same. But those are excellent practices. Those are excellent.
Thanks.